In this video, I'll work through some sample problems with proofs about numbers. First, we have a couple of problems where we're practicing with the division theorem. So the division theorem just talks about quotients and remainders. It says when you have any two integers where the second integer is positive and not zero, that you can divide the first number by the second number and you get a quotient and a remainder. So in this first question, we're being told that we're dividing 18 by 7. And we want to know what is the quotient and what is the remainder. So we do this in the normal way. We think of 18 divided by 7, which looks like this. 7 goes into 18, 2 times 7 is 14, subtract, and we get a remainder of 4. So this would tell us that 18 equals the q, the quotient is 2, the b, the divisor was 7, and the remainder was 4. So there's my a, there's my q, there's my b, and there's my r. Now, alternatively, another option that you have, especially when the numbers get big, is to use a calculator. So the calculator would tell us that 18 divided by 7 is about 2.57143, and so on. So what we can see is that the number in front of the decimal point, that's my quotient, that's still my q. And then this number after the decimal point, that's telling me that I've got some remainder, but it doesn't exactly tell me what that remainder is as a number, as an integer. So what we can do is we can take our equation that we know that we want, a equals qb plus r, and at this point we know everything but r. We know that a is 18, we know that q is 2, we know that b is 7, and we don't know what r is, but we can solve that and figure out that r is 4. So we can get the same information with a calculator, just have to do it in a little bit different way. Now when the numbers are negative, it gets a little bit trickier, right? So again, we're dividing negative 1,234 by 10, and we want to know what's the quotient and what's the remainder. The key thing to remember here is that the remainder must be greater than or equal to 0. We can't have a negative remainder. But besides that, we could think to ourselves, okay, I'm dividing 1,234 by 10, ignoring the negative sign temporarily, and that's going to go in 123 times with a remainder of 4. So if this were positive 1234, our quotient would be 123. But if we try to set up that remainder with a quotient of 123, it doesn't quite work. Because if we set up our equation, a equals qb plus r, if we try to make our quotient be negative 123, what does r turn out to be? Well, when we try that, we get negative 1,230. We add that to both sides, we get a remainder of negative 4. And we can't have a remainder of negative 4. So what we have to do is we have to make our quotient be 1 lower. And that's going to give room for a bigger remainder. So if our a is still negative 1234, our quotient is going to be negative 124. We've subtracted 1 from the thing that we thought was our quotient. And now when we try to figure out what our remainder is, it's going to turn out to be the right size of number. Add this to both sides, we get that the remainder is 6. And 6 really is greater than or equal to 0 and less than 10. So our r is 6 and our q is negative 124. Now we're getting into proofs involving divisibility. So this first one is asking us to prove that if a is divisible by 4 and b is divisible by 5, then a times b, is divisible by 10. So our hypothesis is that a is divisible by 4 and b is divisible by 5. So that's where we're going to start our proof. We're going to let a and b be integers such that a is divisible by 4 and b is divisible by 5. So a good second step here, right? That's always a good first step. A good first step is to write down making the hypothesis true. And a good second step is to use the definitions of the words that were being used. So in this case, we're using the word divisibility, so we're asking ourselves, what does it mean to say that a is divisible by 4? So since a is divisible by 4, what that means is that a equals 4 times k for some integer k. And similarly, since b is divisible by 5, b equals 5l for some integer l, using a different letter because it's probably a different integer. And now we're ready to start thinking about our conclusion. Our conclusion says a times b is divisible by 10. Well, we've got an expression for a, we've got an expression for b. Let's plug those into a times b and see what happens. So now we compute. A times b, well, a is 4k and b is 5l. So when we multiply that out, we get 20kl. Now, is that divisible by 10? What would we have to be able to do to show that that's divisible by 10? Well, we have to show that it's 10 times an integer. So we have to be able to factor out a 10. And in this case, we can. Since 2kl is an integer, because k and l were integers, a times b is divisible by 10. And so we're done with the proof. So that's the basic structure. Start with the hypothesis, then explain what the words in the hypothesis actually mean, and then start working towards the conclusion. So another if-then statement here, we have proof that if n is not divisible by 3, then n squared plus 2 is divisible by 3. So here our hypothesis is to say let n be an integer that is not divisible by 3. Now we know what it would mean for n to be divisible by 3. That would mean n would be 3q for some integer q. But what does it mean for n to be not divisible by 3? Here's where the division theorem can help us. By the division theorem, we know that there are only so many ways that n can be divided by 3. The remainder, when n is divided by 3, can only be one of 3 things. It can only be 0, 1, or 2. And since n is known to be not divisible by 3, that actually eliminates one of those 3 possibilities. Since n is not divisible by 3, the remainder is not 0. And that leaves 2 possibilities. So we're going to break those 2 possibilities into 2 cases. So this is a proof by cases. In case 1, if the remainder is 1, that means n equals 3q plus 1. That's how we write that in terms of the division theorem. N equals 3q plus 1 for some integer q. And now what would that tell us about our conclusion? What we hope is that, in this case, n squared plus 2 is divisible by 3. So let's look at what n squared plus 2 looks like. We know n is 3q plus 1, so that's 3q plus 1 squared plus 2. We work out some algebra, that's going to work out to be 9q squared plus 6q plus 1 plus 2 is plus 3. And then we can factor a 3 out of that. Remember, we want this to be divisible by 3, so we're looking to be able to factor a 3 out. And we can. So since 3q squared plus 2q plus 1 is, in fact, an integer, that means that n squared plus 2 is divisible by 3. And now we do case 2 in a very similar way. So case 2, this is where n equals 3q plus 2 for some integer q. That's the other possibility, the other possible remainder. And now we would say that n squared plus 2, that's going to be 3q plus 2 squared plus 2. Work all that out, we get 9q squared plus 12q plus 4 plus 2 is plus 6. And then again, we can factor a 3 out of that. We get 3q squared plus 4q plus 2. And since that's an integer, so since 3q squared plus 4q plus 2 is an integer, n squared plus 2 is divisible by 3. And so again, what we've proved now is that n squared plus 2 is divisible by 3 no matter what. No matter which case we have ended up in, we know that now n squared plus 2 is divisible by 3. So that's how we write our conclusion. Our conclusion says, therefore, in every possible case, right, because there were only 2 possible cases. There were 3 cases initially, and then we realized that one of them was impossible. So in every possible case, n squared plus 2 is divisible by 3. And that's the end of the proof.